Introducing scalar field, vector field, grad, that's a symbol for grad, div, that's a symbol for div, and coil, that's a symbol for coil. Scalar field. If you have a point in space, point P, phi, P is a point in space that has a scalar function, phi. So the scalar function of P is phi, and that will generate a scalar field. A scalar field is just a number or value. So this vector here has a unit vector j in the y direction, a unit vector k in the z direction, and a unit vector I in the x direction. Unit vector implies I is 1, k is 1, and j is 1. Example of a scalar field are temperature, potential, energy. So you can see like a mountain here, and the top of the mountain is 90, so that's the highest value for the scalar field, and you can go from 50, 80 to 90, so this is a direction you're going if you're climbing up the mountain, and you're going that way, and these are all the scalar field. You can get possible ways you can get to the mountain. So that's the number or value or magnitude, and that's what you call scalar field. Now let's look at a vector field. So we have a point P here, and that point P has a vector function. Because of that, it will have a vector field. So example of a vector fields are force, displacement, velocity, acceleration. So a vector field is with size and direction. Grad. Grad stands for gradient of a scalar function. So if a scalar function phi is continuously differentiable with respect to its variable x, y, and z throughout a region, then the gradient of phi, grad phi, is equal to partial derivative of phi with respect to x in the I direction plus partial derivative of phi with respect to y in the j direction plus partial derivative of phi with respect to z in the k direction. So remember, phi is a scalar function, just a number. The coil d is a partial derivative, and grad phi is a vector function. Grad is a measure of how quickly a particular quantity changes over a small distance in one of the three variable directions, either in x direction or in y direction or in z direction. Here's an example of phi. So applying grad function to phi, and this is what we get. We get the partial derivative of the phi, which is that one here, in I direction, plus partial derivative of phi in the j direction with respect to y, and the partial derivative of phi in the k direction with respect to z. So what that meant is we're differentiating with respect to x while the other variables are constant. So 2 times 2, that's 4. Then we get 2 minus 1, that's 1. And then y and z cube are constant, they just stays in the direction of I. Plus, again, we differentiate with respect to y by keeping x and z constant. If you differentiate y, you get 1. So therefore you get 2x squared z cubed j. And then we differentiate with respect to z by keeping x and y constant. So you bring the 3 down, 3 times 2, that's 6. And then 3 minus 1, that's 2. That's how you get that. Now let's look at notation. Grad on phi, applying grad to phi, this is what we get. This is what grad is. So grad is a vector differential operator, and we can represent grad as with this symbol. So this symbol here is equivalent to or identical to the partial derivative with respect to x plus partial derivative with respect to y plus partial derivative with respect to z. And the symbol is pronounced del or Nabla. Del cannot exist on alone because it is an operator. It must be applied to a scalar function, and that is a scalar function. So grad is basically del when applied to, so when you apply del or Nabla to a scalar function, and you call it grad, because you're finding the gradient of the function. If f is a vector function and we're applying Nabla to f, that has no meaning. So when you apply a Nabla to a scalar function, it has meaning, and that is an example here, grad on a scalar function, and I will give you that. So remember, phi is a scalar function. Applying Nabla to phi has meaning. Applying Nabla to a vector has no meaning. Here's an example. If phi is equal to x squared y z cubed plus x y squared z squared, find the grad of phi at the point P equals to 1, 3, 2. So here we apply grad to phi, and then we get this equation here. And so at each point of the phi is now replaced with the value of phi. So here is the phi here with the derivative. So what we need to do is differentiate the phi with respect to x. So if we're differentiating that and keeping y and z constant, we're going to get 2x. So that's 2x. And the rest is constant. And we're going to differentiate that with respect to x, which is going to get y squared z squared in the I direction plus, now we're going to do the j direction with respect to y. And so we're differentiating this, ignoring x and z, we'll differentiate y. If I differentiate y here, I get 1, so that'll be x squared z cubed. And if I differentiate this one with respect to y, I get 2x y z squared. That's for j direction. Now to do it in the z direction, the k direction, all I need to do is differentiate with respect to z. So that'll be 3x squared y z squared. That's 3x squared y z squared plus 2x y squared z. Now we need to work out grad for that point. This is x, y, and z. And so to put that, we just place x value in there and y value and z value. And in doing that, we get 48 plus 36 for that one. And for that one, I get 8 because when x is 1 and z is 2, 2 cubed is 8, 8 times 1 is 8. And then I do the same thing here, and then do the same thing there. I get 36 for that and 36 for that. Now to work out the final value, we add that up to get 84i plus 32j plus 72k. So therefore, the grad on a scalar function, we now give a new vector, a vector function, which is 4 is a common factor. So 4 out, you get 21j plus 8j plus 18k. Now that's a vector. So we've turned the scalar function into a vector function. So that's the gradient of phi. And that will have a vector field. Now let's look at divergence of a vector function. The operator Nabla dot can be applied to a vector function to give the divergence of A, where A is a vector. So now applying div A, which is Nabla dot A, will be equal to the Nabla dot the vector A. So the dot here is a dot product or scalar product. That means dot. Here's an example. This dot product is applying this equation where a vector A dot a vector B will be equal to magnitude of vector A times the magnitude of vector B cos theta. Now, if you have dotting I and I, well, I and I are parallel to each other and the angle between them is 0. Therefore, but I is a unit vector. A unit vector means I is 1, j is 1, k is 1. Therefore, so I dot I will be, we'll put a dot there, I dot I will be 1 times 1 cos of 0. Cos of 0 is 1, so that will be 1. So I dot I is 1. That means they're parallel to each other. Because they're parallel to each other and the angle between them is 0, the dot product is 1. J dot j is 1 and k dot k is 1. But what about I dot j? Well, I dot j will be 0 because the angle between I and j is 90 degrees. So cos of 90 is 0. So therefore, I dot k will be 0, j dot k will be 0, which meant that when we're multiplying these two vectors together, it's only the I coefficient will multiply with the I coefficient of the vector A. And therefore, but the I coefficient times the j coefficient will be 0. Likewise, the j multiplied by any other coefficient other than j will be 0. That's what this is telling us. So this vector product will be the coefficient here times the ax and the coefficient here times the ay and the coefficient here times the az. So now that we're doing div A, which means it's a dot product of A, and this is what we get. We're multiplying the Nabla with the vector by a dot product, and that meant that we can only multiply the partial derivative with respect to x times ax plus partial derivative with respect to y times ay plus partial derivative with respect to z times az, because only the I and I will give 1, j and j will give 1, and k and k will give 1. That's why we get that. But if you do I and j, we get 0, which means that disappears. J and k will be 0. That disappears as well. Because naturally, you multiply, you expand by doing that times that, that times that, and that times that. That times that is 1. I times I is 1. So therefore, that says, and that times that, I times j will be 0, which meant 0 times the coefficient will be 0. That's why they disappeared. So note, the grad operator, grad, acts on a scalar function and gives a vector function. The div operator, which is this one here, it is Nabla time a dot, act on a vector function and give a scalar function. So that will be scalar value. Here's an example 1. You have a vector. We need to find the div of vector A, which means divergence of vector A. So applying the Nabla dot A, which means divergence of A, we multiply it by the operator vector, differential operator vector, times the vector itself. Just to remind you, this is what the dot product is doing. If you have a vector A, you dot it with the vector B, it will be equal to magnitude of vector A times magnitude of vector B cos theta. But in this case, I, the vector I, are unit vectors. So that means I is 1, j is 1, and k is 1. So if you have I dot I, you're going to get 1 times 1, cos of 0, that's 1. So that stays, which means we can then multiply that with that, and that with that, and this one with k. So we multiply the respective coefficients. So that meant that we're going to x squared y will be multiplied by, so we just multiply that by that, so we get x squared y, and we multiply the partial derivative with respect to y by the minus xyz, that is j times j, so we get that. And we multiply partial derivative with respect to z, which is k, by k, so that be by yz squared. So now what we do is differentiate this one with respect to x, so that be 2xy, keeping y constant, or z. We differentiate this one with respect to y, so that be, if you differentiate y, you get 1, so that be minus xz. If you differentiate that with respect to z, so that be 2yz. Div of a will be 2xy minus xz plus 2yz. So that's a scalar function, because if I put a value for y and x, I'll get a number. And if I put a value for x and z, I get a number. And if I put a value for y and z, I get a number. So because I'm getting a number here, the divergence of a will give a scalar function, a number. Example number 2. We've got a vector here. We need to find the divergence of a. So again, div of a will be Nabla dot a, and that will be equal to Nabla dot a. So now what we need to do is to find a partial derivative of this with respect to x. So that will be 2 times 2, that's 4, and 2 minus 1 is x, so you get 4xy. And this is minus, I'm going to differentiate with respect to y, so that will be 2xy plus 3y squared z. And then if I multiply all that by 2 minus 2, I'm going to get minus 4xy minus 6y squared z. And then the final one is to partial derivative with respect to z. So I'm going to differentiate the z here, so that will be 2 times 3, that's 6y squared z. That will be 6y squared z. And so now, and then if you work this out, you can see that that cancels that, and that cancels that, and so we get 0. So note, this is a special case, where if you do div or divergence of a, you get 0 at all point. That means a is called a solenoidal vector. So what's a solenoidal vector? A solenoidal vector is a vector that has no source or sink. Well, if you have a positive charge and the field are coming out of the positive charge, that's what we call source. And the field is going to the negative charge. And you can see the arrow going to the negative charge, and that's the sink. But if you look at a magnet, the magnetic field is coming out of the North Pole and going into the South Pole. Now, this one looks like a source, and that looks like a sink. But the source and the sink won't happen unless the two North and South are joined together. Hence, the field actually goes through. Because if it goes through, so this is not a source anymore, and therefore the sink doesn't exist. So this is what we call solenoidal vector. This vector field here have no source or sink, no lone source and no lone sink. This is a lone source and that's a lone sink. So for an electric field, this value will not be 0, but for a magnetic field, that value is 0, always. Curl of a vector function. The curl operation, which is del cross, acts on a vector and gives another vector as a result. Here's a vector, then curl A will be equal to Nabla or del cross A. Curl A, which equals to Nabla cross the vector. So that's a cross. A cross is a cross product of vector product. And here's the equation for a cross product of vector product. If you have two vectors A and B and you cross them together, it will be equal to the modulus of A times the modulus of B sine theta. Now, I and I are parallel, which means the angle between them is 0. But I is 1 I is 1. So modulus of I is 1 times sine of 0, and that's 0. J and J, K cross K will be 0. Using a cross product here, you have to do I cross J. I cross J will give you K. I and J will be 90 degrees apart because they're both right angle. Because they're right angle, sine of 90 degrees is 1. It's actually sine of 90 degrees is going to be, in this case, it will be K actually. So it's 1. That will be this vector direction, and that will be K. So I cross J will be K. J cross K will be I. And K cross I will be J. I cross J is K. J cross K is I. K cross I is J. But if you go back in the opposite direction, K cross J is minus I. J cross I is minus K. I cross K is minus J. So that's what cross product does. Because don't forget these vectors I, J, and K are unit vector, which means I is 1, J is 1, K is 1. Unit means 1. Coil A equals del cross A, and this is del crossing A. We need to apply determinant method. And to apply determinant method, we put it in a matrix format. I, J, K, these are the I, J, K, and then the del and the vector. This is a modular sign. This one means positive, this is negative, and that's positive. Now applying the determinant, we can see now we select I, so that's I, plus I because of that plus, and then we cross a line here, and we cross that, and what that meant is we are now going to multiply the 2 by 2 matrix here, so that'll be AZ times partial derivative with respect to y. AZ times partial derivative with respect to y. Then we have to do minus AY partial derivative with respect to z. So that will be AY partial derivative with respect to z. And then once you've done that, then we move on to j. Now we want to find j. So j is minus, so we say minus j because it's minus j. And then we draw another vector line here. So we draw a line here and line across. So that means that we're now going to use this 2 by 2 matrix here. Coefficient vector AZ times partial derivative with respect to x, that's that one, minus AX times partial derivative with respect to z. And then close bracket. And so now we've done that. Now we need to do k. Now for k, we get a line, we draw a line like that, and because it's crossing there, so we're looking at that vector here indicate in that direction, so that's plus k, that's plus k, and then we now need to multiply these 2 by 2 matrix. So that would be, we always start from the right up diagonally, so that would be AY times partial derivative with respect to x and minus AX times partial derivative with respect to y. So curl A is a vector function. Remember, A is a vector and curl is basically del cross. And if curl A is equal to 0, then A is said to be irrotational. So the curl represents the rotation of a vector field, and direction of curl is the axis of rotation, and the magnitude of curl is the magnitude of rotation. So the curl represents or is a measure of circulation of vector field. If you have your right hand and you fold your thumb pointing up and your finger is coming in anti-clockwise direction, then we can represent that as coming out of the paper, and that's how you draw that. And that will be your vector field, and that's the rotation in that direction, which giving you a vector field in this direction. Again, if you use your right hand and there's a rotation clockwise direction, again, if you use your right hand, your thumb pointing downward, this will be in a clockwise direction, And the way to draw that is to do a cross in a circle. That means going into the paper. This is the direction of the vector field. Here's an example. If you have a vector A, find coil A at the point 1, 3, minus 2. Okay, so now we're doing coil A, and that would be del cross A as a cross product or vector product. And so we put it in I, J, and K, where this is plus, minus, plus. We write the Nabla here and the vector there. This process is what we call determinant. So this is coming from this one here, and what we've done is we take I vector, so we cross that out and we do AZ times derivative or partial derivative with respect to y, and that's what you get here, minus, and we do AY partial derivative with respect to z. And then we look at j direction, we cross that out, and that's a minus, so we say minus j. Again, partial derivative, we always go from right to left, partial derivative of AZ with respect to x. So that's AZ with respect to x minus partial derivative of AX with respect to z. So AX with respect to z plus, and now we're looking at K now, so we draw a line across there, and therefore we're looking at these two metrics. Again, AY partial derivative with respect to x minus AX partial derivative with respect to y. And that's what we've done. That's how we got that. And now we're going to differentiate AZ, which is, this is AZ here. We differentiate that with respect to y. So we're expecting, sorry, this is AZ. We differentiate with respect to y. So we're expecting minus x squared z. And that's why you get minus x squared z. Because we only differentiate with respect to y, so we differentiate y. We get 1. Now we need minus, so this one we need to differentiate with respect to z. We're differentiating y, ay with respect to z, and there's no z here, so that'll be 0. All these are constant, so that'll be 0. Minus, the minus here, j, open bracket. Now we want az with respect to x. So we're looking at az with respect to x. So that'll be 2 times x, and so that'll be minus 2x, because it's a minus here, yz, and so we differentiate x squared, we get 2x, minus ax with respect to z. That will be a constant, so that will be minus, so that will be 2x squared z, so that will be plus 2x squared z, because it's minus, minus, and minus is plus, so that's plus. And the next one will be this one here, ay with respect to x will be 2x, because that is a constant, so that will be 0. And then we want minus ax with respect to y. Ax with respect to y, so that will be 4y cubed. That's just minus, by the way, because it's minus here. So it's minus 4y cubed, because it's minus here. And that's how we got that. So after getting that, now we need to use this point of P. And that point has coordinate 1, 3, minus 2. So we put in here 1 minus 2. That obviously gives us plus 2i. And then we put in here 1, 3, and minus 2 here. And we got 12 minus 4. That's 4. That's minus 4. And that's 12. And this one gives 2, because 1 times 2 is 2. And then that one gives, well, 3 cubed, that's 27 times 4, 108. And so now the coil A, or del cross A, will be equal to 2i minus, that's minus 12, plus 4 is minus 8j, minus 2 minus 108, minus 106k. Now we can see that when we cross a vector, when we curl A, which is a vector, we get another vector. So summary, a grad operator is operating on phi, and that gives a vector. So gradient, grad, when you're operating on a scalar, you get a vector. And that's a scalar field, you get a vector field. Div operator, which is divergence on A, we give you a scalar. A is a vector and you get scalar. So you get divergence on a vector, you get scalar value. C, coil operator, which is del cross A on a vector, you get another vector. So that's coil del cross on a vector, you get another vector. So scalar function, which is the phi, grad on phi, will be that function there, del phi, and that's how we write it. The vector function A, we write it like that, and we can do two things on the vector function. We can do divergence of A, which is the Nabla dot A, that's a dot product or scalar product, and this is what we get. We get scalar value. That's the divergence, so that's a scalar value. Another thing we do is coil A, which is the del cross A, which is cross product or vector product, and this is how we work it out using determinant. So application. The application here is on a gravitational field, and that gives you minus when you apply the del on a function, scalar function, and that this scalar function here is called gravitational potential, and it's negative because it's in the opposite direction of the gravitational field. So that's why that's negative. So if I draw a gravitational field, which is an attraction field, there we go, so that's attraction, that's a field, that's attractive force, and the gravitational potential minus del phi, and that is negative because it's in the opposite direction, and so that's why that's one application there. Another application is a Maxwell equation, and that deals with electric and magnetic field. The first part is when you divergence of electric field, we give a value because it's got a lone source where positive is coming out, that's a divergence, and where it's coming out is positive, and where it's coming in is negative, that's a lone sink, and this one is density over epsilon naught. Another Maxwell equation is when it's applied to magnetic field, and you doing a divergence of a magnetic field, you get 0, and B is a solenoidal, which meant that there are no lone source or sink. The divergence of a magnetic field is always 0. Another Maxwell equation is when you cross vector product here, the del with a cross with electric field, you get minus change in magnetic field over time. So this one shows a link between electric and magnetic field. That shows a link between electric and magnetic field.